Hey, this is Peter Estes with Valley CAD. I'm going to be showing you guys a pre-recorded video that we created when we did a live webinar all about CFD and Simulia. Before we hop over to that pre-recorded video, I want to thank Reza with Dassault Systems who assisted us during that webinar, as well as everyone else that attended the live session as well. So let's hop on over to that webinar now and learn some more about CFD and Simulia. I'll see you over there.
For CFD, namely SolidWorks Flow Simulation, Fluid Dynamics Engineer on the 3D Experience platform, and the Xflow. And then I'll wrap up with a summary, and hopefully there is time for a quick QA as well. So, obviously, CFD is being used in so many, practically every industry, from industrial equipment, aerospace, automotive, and consumer products, life sciences, high tech, and then some others. As you will see, so Dassault Systems cover many different applications falling in these different industries. And for some of these applications, all the three products that I mentioned in the previous slide, they are good. For some of them that are a little bit more specific, maybe two of them are more suitable, and sometimes just one of them is really kind of, handling that particular application. So this just animation, it's cool, free surface flow that we have done, there's the experiment and the simulation is kind of overlaid. Now, free surface is not a typical application, but again, it's kind of cool to kind of have a look at simulation on top of an experimental test here. Now, as I mentioned, again, so many different industries, but to kind of narrow down to one industry, I kind of chose the automotive industry. And it is not because I'm assuming people attending today's webinar, they are all in the automotive industry. From the list of the people who were planning to attend, I saw that there is a very diverse group of applications and industries, actually. And the reason I chose automotive is that it is something that everybody can relate to. And also, the beauty of finite element analysis, FEA, and computational fluid dynamics, CFD, is that the principles and the approach is almost identical in any of these applications and industries. It's just the minor details. For example, when you are thinking about heat transfer, you can think about high-tech, a PC box, or you can think about the HVAC in a building, or some heat-generating components in a car. Again, the concepts are the same. There are heat sources, etc., and they have to be dissipated. But here, let's say, for the automotive industry, you see really kind of the range of different things can be done with simulation, from cabin comfort to battery engineering to aerodynamics of the car, and many more. Now, Dassault Systems has a long-term commitment to simulation. Again, I'm not going to go through all these different kind of companies that we have acquired throughout the years. Obviously, Dassault, we develop a lot of software internally as well, but that is kind of the combination of, developing software internally as well as acquiring companies that are well-known and are specialized in a particular area. Now, again, you see the long list. The flagship product on the structural side of it is Abacus, that is very well known in in the FEA side in the industry, having been around since 1978. Obviously, SolidWorks simulation products, many of you are familiar with, but just keep in mind that there are lots of different solutions that are available as part of the Dassault Systems portfolio. Now, focusing on computational fluid dynamics, from the range of solutions that we provide at Dassault, we have SolidWorks Flow Simulation, the main package, as well as the two add-ons on top of it for electronic cooling and HVAC. We have the Fluid Dynamics Engineer role, on the 3D Experience platform that we'll also be talking about, as well as a solution that, two solutions, they were acquired a few years back, XFlow and PowerFlow. Now, on the flow simulation itself, it's a general purpose fluid flow and heat transfer simulation solution. The biggest advantage of that is the integration within the SolidWorks CAD environment, seamless integration there. It is, a design tool, for really kind of mainstream applications, extremely easy to use. It has many capabilities, capturing internal and external flows, incompressible and compressible fluids, Newtonian and non-Newtonian. Non-Newtonian, for example, in some applications in the life sciences comes very handy. Laminar, turbulent, and transitional flows, heat transfer simulation, obviously, rotating regions, free surface, and you saw also an animation earlier, as well as coupling the simulation with SolidWorks simulation for stress analysis. It's a one-way coupling, the one that I'm talking about here. Now, the interface, totally embedded within SolidWorks simulation. So I actually have one simple example that you see here handy. So let me go actually to the program itself. I've already set it up. It's extremely fast and easy to set it up. But because, we have a very short time here in this 30 minutes, I kind of, wanted it to be ready. So in principle, you have a pipe with a ball valve at some angle. And, the setup is, pretty straightforward in terms of the overall kind of definition of the general settings. You define it is an internal problem, and the fluid is water. The rest of the stuff, there are some defaults built into the program that in this particular case, we don't need to make any changes at all. In terms of the actual flow for this particular problem, we specify that 0.5 kilogram per second mass flow is entering the pipe at a constant rate. So it's basically a steady state problem, and it is exiting at the other end at environmental pressure. Again, this is the absolute bare minimum that you need to set up, very, very fast to do that. And then you run the analysis. Again, there are lots of things that you can kind of additionally specify if you need to, or, if you wanted to have additional interaction with the program. But again, because we have kind of wanted to make the program available for non-expert users, mainstream users that are kind of doing simulation as a small part of their job, we have kind of made it as easy as possible. And you notice in this particular case, it's very bare minimum that you need to set up. Now, if I wanted to kind of, for this particular problem, if I wanted to look at some results, so, it was entering from left, exiting from right, one inlet, one outlet, higher pressure at the, at the inlet, and some pressure drop along the way. If I wanted to kind of look at the streamlines of, actually, let me show you a couple of other things here as well. So maybe, show this one here. So kind of the streamlines of the flow, you notice here there is a little bit of recirculation in these kind of dead areas there. And let me hide that. And maybe kind of show you a cut section of the mesh. Again, we don't want to get into any of those stuff. These are kind of the defaults that are generated. But again, you have full control over how the meshing done and all of that. Now, maybe another kind of contour plot here, and kind of switching to some other parameters, let's say velocity. You notice here that kind of uniform velocity coming in, and then kind of the velocity picking up as it is trying to pass through the valve. All right, and again, lots of different post-processing capabilities that are available. Like that. Maybe showing you a surface plot. And again, this is kind of the surface plot of the pressure, high pressure, at the inlet, lower pressure, and some pressure drop in between. And then this one here, a trajectory of the flow, and maybe some cool animation on top of that. Okay, so basically uniform coming in, then bending, and then exiting from the other side, maybe looking at it from the top view. All right, so stop that. Hide it. Now, some maybe surface parameter. So I mentioned that I specified an environmental pressure at the outlet, but from the post-processing, you see that the amount of fluid kind of exiting is minus 0.5 kilogram per second. One inlet, one outlet, obviously preservation of mass. And then, finally, I have here maybe an XY plot. And this is kind of along this particular path that you are looking in terms of the pressure variation. Okay. Now, the beautiful thing about being inside of the SolidWorks environment is that if you wanted to kind of make a change, for example, change the orientation. Let's say the orientation of this valve, you can easily do that again, being within the same SolidWorks environment. Very, very straightforward. Okay, so now let's take this one step further. So you have run the analysis on this model. If you had a scenario that you wanted to kind of extend the model, and here you kind of look at the extension of the pipe that kind of splits into two segments. Now you can think about the short length, you can think about the long length, and maybe you can think about some of these sort of barriers, or they call it flow conditioner, this company Vortaps. So they are kind of straighters that you can put in the pipe. And let's say the goal is an equal flow in both exit pipes at different valve positions. So how do you go about kind of looking at it in simulation? If you basically added that additional piece there and run the simulation, what you are going to see is that, for a short pipe, this is again a cool animation. You see the bulk of the flow kind of exits from the left, or in this case here, looking from the top, the top portion. If you looked at the second scenario where you had the longer pipe, you are going to see that the flow is a little bit better distributed, but still not ideal. Okay. And if you look at the third scenario with those Vortaps, you are going to see that you can kind of force the flow to be distributed, much better in the two segments of the pipe. Now, kind of looking at it numerically and the comparison between the three cases, how they are distributed, you see that there's a big difference in terms of the amount of flow between the two exits, the outlets. In the short pipe, less so in the longer pipe, but still quite huge. But if you use that remedy of the Vortaps, even with the shorter pipe, you get a far better distribution, almost kind of identical flow rates from the two segments. And again, this is really the beauty of simulation, that you can look at this scenario very easily, with the program within a few clicks. All right. Now, talking about another application, this one here has a thermal kind of side to it. It's a box with some sources of heat. Now, again, I mentioned, this is a box, from high tech. You can think about that, you have a similar situation if you're thinking about the HVAC system in a building. The dimensions are different, the heat sources are different, but the concept is almost identical. All right, now, in this particular case, what is the scenario that we are trying to simulate? It's basically a package design and fan configuration. So we are kind of this, we have some thermal constraints. So there are particular components that are critical, and we want to make sure that the temperature of these components do not exceed certain values. We have some design considerations. One is the packaging design, and the other one is about the number of fans and the location of the fans. And the objective is the minimization of the buildup of heat, so basically kind of controlling the maximum temperature, and also kind of trying to get away with less fans and trying to kind of position them better. Okay. So how did we go about doing this? So first question, to vent or not to vent, and then we run the two scenarios, and then extract the data for those components that are critical, and we notice that in principle, we can get away with no vents, so we can stay below that those maximum critical temperatures. Now, obviously, that is a better solution because of many reasons, manufacturing costs and all of that we can save, but also in terms of usage, that it's obviously more flexible if there are no vents rather than if there are vents. Okay, so then we look at the scenario. Okay, combination of these different cases of one vent located at 3 different places, 2 vents with different combinations, and comparing that to the case of 3 vents. And we run everything, and we put everything, all the results together, make a comparison, and we notice that some of these solutions are not acceptable. The ones with the 1 vent, and some of the 2 vents they are okay. And the best solution is a combination of B and C. So we basically do not need all the 3 fans if we place the B and C and keep those 2. I'm not going to go to the program itself. Again, the setup is a little bit more, a few more clicks, but otherwise the concepts and the approach is almost identical to the previous example. So here are some animations of a few different examples from fluid flow, liquid flow, again in a more complicated valve system. This one here, some sort of a manifold design. And again, the extension of that first example that I showed you earlier. This one here is the wind loading on a semi-submersible rig. So basically you run the flow simulation, it calculates the pressures and forces on the structure, and then you can take those values to a stress analysis with SolidWorks simulation and look at stresses, displacements, and so on. This one here, flow of mud and coolant. This is again a combination of a few different applications. Again, some visualization of post-processing results, again in different applications there. And again, a few more. And this is what I was mentioning earlier, that again, that PC box or the electronic cooling example that I showed you earlier, we can think about that as the HVAC of a full building airflow as well. Again, very, very similar concepts. And a little bit kind of making it fancier. So the one on the top is some radiation problem, thermal radiation. This one here on the bottom is from life sciences, where we are looking at an inhaler. So basically, if somebody had asthma, using an inhaler at some distance from the face, as that releases, you want to have a nice distribution in front of your face, around the mouth and the nose area. And you can also do a transient simulation of the breathing and see how that pure oxygen, for example, can mix with the actual air. All right, so the second kind of, I spent a little bit more time on that flow simulation because of the integration within SolidWorks, and many people kind of use that, but also because, it's the first example, or, it talks about some of the aspects of CFD that is also applicable to some of these other kind of packages that I talk about. Now, this one here, fluid dynamics engineer, we have this internal kind of naming for it, FMK, just for a shorter kind of reference. But you see the applications, or kind of the capabilities rather, are very similar in many ways to flow simulation. Again, I'm not going to go through all the list given here, but just by first glance, you notice that many of those capabilities that I mentioned earlier, they can also be run with fluid dynamics engineer as well. Now, What is one big benefit or difference between fluid dynamics engineer and flow simulation is the 3D Experience platform. And these are some key benefits of the platform in terms of having a unified user experience, extending these capabilities to not only engineering, but also manufacturing, sales, and marketing, creating a social collaboration environment, having everything accessible on cloud, which again comes with its own advantages, and packaging them by roles. And this is why this particular role, we call it Fluid Dynamics Engineer. And we have many other roles in structural and beyond that are available. Now, again, I mentioned the difference between the two in terms of desktop versus cloud. But flow simulation, again, the biggest advantage is the integration within SolidWorks, extremely easy to use and user-friendly, nice post-processing, and so on. FMK, the biggest advantage is that, the platform side of it, cloud, the fact that it can solve much bigger problems, more complicated models, higher accuracy, but also it has some functionalities, in terms of, different meshing technology, additional turbulence models, etc. And finally, it integrates kind of better with other DS solutions and more appropriate long-term, if you like. Now, I mentioned about meshing. Again, this is just a view of it. I'm not going to get into the details of it now, but there's kind of a basically different meshing behind the scene that is employed to run the CFD. So this one here, I'm not going to kind of run the whole 5-minute video, just for you to kind of get a feel about the interface. You see here, there's an assistant panel that kind of helps you set up the problem, quite handy. And then, again, I don't want to kind of run the whole thing continuously, but you just get the point in terms of, how the interface looks like. These are some kind of if you like, animations and applications. Again, many of them in the automotive industry, again, because of the very reason that I was mentioning earlier. I chose these ones here, but the same can be extended to any industry and any application. Okay, couple more here. Again, having run that with FMK. This one here, an exhaust catalyzer design, and the one on the right, thermal design. Okay, now the third package that I mentioned earlier is XFlow. And again, I'm not going to go through all these detailed differences between the two packages, but just to kind of set the stage. And you can think about flow simulation to be on the left side as well. So kind of bundle it in terms of the way you contrast flow simulation and fluid dynamics engineer on the left with the XFlow on the right. So these two, flow simulation and the FMK, fluid dynamics engineer, extremely powerful for mainstream applications, absolutely fantastic for steady state problems, and some, again, the details of it, I'm not going to get into that in terms of Navier-Stokes versus Lattice-Boltzmann. But the one on the right, XFlow, kind of uses a different methodology. Again, this Lattice-Boltzmann is something that is a little bit newer. Navier-Stokes has been around for more than 67 years from the inception of these numerical approaches of finite element analysis and CFD. This one here on the right is much newer, and it's really kind of geared towards a more kind of specific applications like highly transient kind of turbulent flows. And you see that in some of these animations that I show you. So let's say transient aerodynamics, some of these applications in terms of these ocean waves, kind of wind turbines. This one here is the turbulent, airflow wind, or even kind of, high-speed wind around stadium. These ones here, again, you see, highly turbulent problems highly transient problems that, obviously a steady state solution is not going to be good for that. That is something that the XFlow, with that methodology, Lattice Boltzmann, is much better suited for. Also, another kind of area is this, fluid solid interaction, FSI, with really moving parts. I mentioned in flow simulation, you can do a one-way fluid structure interaction, in the sense that you run the flow analysis and then you export, or the program does it. You tell the program to kind of push the results in terms of pressure and force distributions to the stress analysis package, and you run a stress analysis there. That is a one-directional kind of interaction from flow into fluid. Whereas, if you want to do a full-blown FSI, or if you have, for example, moving parts, then you have to kind of look at the problem differently. These ones here, again, some fancy applications. In this case here, a car overtaking a truck and looking at all the airflow around the car and the truck. This one here, in terms of the lubrication, and again, quite complex transient problem to capture with the other packages. And here the tire rotating on a wet surface there. Again, from XFlow, what you need to remember is kind of highly transient turbulent flows and moving parts at this point. And with this one here, again, my last slide, thermal flow in a T-junction that was run in XFlow. Now, again, this one here, you can run it in flow simulation and fluid dynamics engine. As a matter of fact, I do have it there in terms of a steady state problem. But if you want to look at really kind of the full-blown transient, kind of highly turbulent flow, then you are much better off with XFlow. With that, I think we are kind of perfect in time. I'm just going to summarize in 1 minute, and we are going to be exactly at the 30-minute time slot. So what you need to remember, obviously there was a lot of material that I tried to kind of squeeze in, but the main things to remember is that CFD simulation in the industry, it is being used very widely. The benefits are kind of self-explanatory, and I'm sure by attending this session today, you subscribe to those benefits. Just keep in mind range of application in the industry for CFD. Dassault Systems offers a few different solutions for that, quite diverse, with many similarities, but also some differences. SolidWorks flow simulation, the biggest advantage is the CAD integration and the ease of use. The fluid dynamics engineer, the biggest benefit is the integration within the 3D Experience platform, and that brings collaboration, cloud, and scalability. Now, again, you can kind of, link it to your CAD, but obviously with flow simulation being totally embedded within the SolidWorks interface, that's going to be easier. And finally, XFlow with the kind of the LBM methodology that kind of opens up applications for highly transient flows and moving mesh applications. With that, again, thank you very much for attending this, and I pass it on to Peter.
Pretty awesome, huh? Reza, thank you again for your assistance with that webinar and showing us some awesome functions and tools with using SolidWorks simulation, flow simulation, the CFD portion, as well as what's offered on the 3D Experience platform. If you want to learn more about SolidWorks as well as the 3D Experience platform, please reach out to the Valley CAD team. You can call us on our office line, which is 559-726-2276. You can also reach out to us. That's info@valleycad.com. Or you can easily just go over to the Valley CAD website and you can see the contact us there. You can also see some of the other services that we provide as well. So thank you again for watching this video. Have a great rest of the day and make sure you learn something new. See ya.